Here are our Chapter 17 Voice Enhanced Lecture Notes. So the chapter I have divided into these parts. This is our outline, what I would have written on the board. It is arrangements, microstates, and disorder, thermodynamics. First law of thermodynamics, that'll be a review from Chemistry 1. Spontaneity and Gibbs recognition, entropy, delta S of the system and the third law of thermodynamics, delta S of the surroundings, delta S of the universe, delta G, the second law of thermodynamics, and two more delta G functions, and then a summary. So going into arrangements first. Arrangements, microstates, and disorder. So imagine that we throw an ordered deck of cards into the air. Let's say that they are perfectly ordered. King to ace, suits, and all that. So we throw them in the air and then we pick up the cards as we find them on the floor. We know that they will not be in the ordered state. We could use the term arrangement for the state, that ordered state. There is only one arrangement for the cards to be in this ordered state, and many arrangements for the cards to be disordered. Probability arguments say that the most disordered state is the state that we will find, or we could say the arrangement that we will find. The state most likely to exist is the one with the greatest number of possible microstates. So that's a new term, microstates, where a microstate we could say is a configuration. Okay, so let's get this under control by working with this situation. We've got a gas, and we know that the gas will occupy the entire flask that it's in. That's because the most disordered state and the state with the most microstates is that one. Okay, so to help us to understand this, we will consider a gas composed of only two molecules, molecule A and molecule B. And we have them in a flask, which is that funny two-part blob that I've drawn there. We will distinguish the gas molecules as molecule A and molecule B. Now, we have several arrangements that we will consider for our two-molecule gas. The first arrangement, or we could say state using that term with the cards, is two molecules on the left side. So that would be both A and B on the left side, as is shown in the table under microstate. There's only one possible microstate of those two molecules being on the right side. I'm sorry, the left side. So only one microstate. So that takes care of the arrangement or the state, two molecules on the left side. The next arrangement we will consider is one molecule on the left side. Well, that could be A on the left and then B on the right, or it could be B on the left and A on the right. What we have are two possible microstates for this arrangement of one molecule on the left side. No molecules on the left side, that's our last arrangement, our last possible state. So we put them both on the right side, but there's only one microstate for that situation. Now what we have is a total of 4 microstates. So the probability of the arrangement two molecules on the left side is the 1 microstate divided by the total of 4 microstates, so that means it's 25% likely. The arrangement where we have one molecule on the left side, well, there's 2 microstates for that arrangement. So we take the 2, we divide by the total, we get a 50% likelihood. And then our last arrangement, no molecules on the left side, there's only one possible microstate, so we would say that that is 25% likely. Notice that 50% likely, greater probability of finding that, the gas being spread out is what gases do, as you know from experience, and that's because it turns out that that's the arrangement that allows for the most microstates. Okay, so we have at the bottom, so the most likely state is where the molecules are spread out. As the number of molecules increases, there are more and more microstates where the molecules are evenly spread out. So we will test that idea out by looking at a situation with 3 molecules in the flask, molecules A, B, and C. So we'll run through it the same way. We will look at different arrangements. Our first is 3 molecules on the left side. There's only one possible microstate with all 3 of them on the left side. We'll come back to this other information under the probability column when we're done with looking at all the arrangements. 2 molecules on the left side is our next arrangement, and we can have A and B over there with C on the right, or we can have A and C on the left with B on the right, or we can have B and C on the left with A on the right. So there are 3 microstates for finding this arrangement. Some term that I'll introduce here is this big W. W is the number of microstates. So we have 3 possible microstates for this arrangement of 2 molecules on the left. Go back to the upper one, 3 molecules on the left. That has only one possible microstate. So the value there for W is 1. I guess you could say W is kind of like waves, the possible microstates. 1 molecule on the left side, well, we have the possibility of A there, B and C on the other side, or B on the left, A and C on the right, or C on the left, A and B on the right. So we have 3 microstates for this arrangement. That means W is 3. No molecules on the left side. Well, there's only one possible microstate. W is 1. So if we count all of our microstates, 1, 2, 3, 4, 5, 6, 7, 8, we get that there are 8 microstates. Well, 1 microstate over 8 is 12.5% likely for our first arrangement. 3 over 8 is 37.5% likely for the second arrangement. And for the third arrangement, 1 molecule on the left, we have 3 over 8 again, we have 37.5% likely. And then for the last one, 1 over 8, 12.5% likely. So notice that spreading out is where the likelihood is much greater. Okay, so now we will go to the situation where we have 4 molecules, A, B, C, and D. Now, why don't you stop this video and run through coming up with all the different possible microstates and number of microstates and the ways, what W would be for each one. When you're done with that, then come back. So what we have is for arrangement 1, all on the left, only 1 microstate, arrangement 2, 4 microstates, arrangement 3, where they're the most evenly spread out, we have 6 microstates, and so on. So that means that the most spread out arrangement, the gas occupying the entire volume, has the most microstates, the greatest probability of occurring. That's the one that's going to occur according to probability arguments. Going back to the 3-molecule one, this first arrangement, 3 molecules on the left. Well, if we looked at this 8 times, we would find it in this arrangement once. If we go to the 2 molecules on the left, if we look at that 8 times, we will find it like this 3 times, and so on. That's another way to think of the probability. You have a lab exercise working with solutions mixing, a dye being mixed into water, and you will analyze it much like we analyzed the gas molecules. Okay, our next section is on thermodynamics, which is basically what this chapter is all about. Thermodynamics turns out to involve all that equilibrium stuff that we learned about. What it does not involve is kinetics. Kinetics has to do with speed, and ultimately that has to do with the activation energy. Whereas thermodynamics has to do with how far a reaction goes to completion, and so forth. Okay, so as you learned in Chem 1, the first law of thermodynamics is that energy is conserved. Energy is not created or destroyed. It is transferred between forms and things. So it might be transferred from a hot brick to a cool brick. That would be between things. Or it might be transferred between forms. That would be from potential energy, like water on the top of a cliff, to kinetic energy as the water speeds up as it falls down the cliff. Okay, energy is conserved. That means the energy of the universe is constant, or we could say the delta E of the universe, the energy change of the universe, the E of the universe final minus E of the universe initial is equal to 0. So a reminder of some terms. The system is what we're focused on. As chemists, that's usually the reaction. The surroundings are everything else that is part of our universe, where the universe is everything. So I've tried to show that in that drawing there. The universe is everything. The surroundings are everything but the reaction, and the system is the reaction. The surroundings, if we're doing a reaction that's, let's say, exothermic, we're doing it in water, in a beaker, maybe we're measuring the temperature with a thermometer, maybe we're touching the beaker with our hands, we would say that the reaction is that dissolving compound, the exothermic reaction. Let's say we're dissolving calcium chloride. It gives off lots of heat as it dissolves. That would be the system. The surroundings would be the thermometer, our hand, the beaker, the water. The universe would be all that together. So the energy of the universe is the energy of the system plus the energy of the surroundings. The energy of the system is equal to the kinetic energy of the particles in it and their potential energy, where the kinetic energy is energy of motion, thermal energy. Potential energy for a chemical reaction is usually the chemical energy or the nuclear energy. We can change the energy of the system by heating it or cooling it. Heating it increases its energy, cooling it decreases its energy. We can also change the energy of the system by doing work on it or by it. If we do work on it, its energy increases. If we do work by it, its energy decreases. We can do both those together. We can heat, we can do work, and so forth. The energy change is equal to just the E final minus the E initial. Remember that term state function. That means it doesn't matter how it got between the initial state and the final state. We just have to know what their energies were to be able to calculate the energy change. So we say that it is a state function. It turns out it makes calculations a lot easier. So we learned in Chem 1 that rather than working with energy of the system, we worked with enthalpy of the system, enthalpy expressed by the symbol H. As you learned in Chem 1, delta H is equal to the heat involved in a reaction when the pressure change in the reaction is zero. That is, if we have a reaction that's giving off a gas, we conduct it in an open beaker so that the gas just escapes to the surroundings and does not cause a pressure change. We like working with enthalpy change instead of energy change because it gets us around the work term, which is sometimes difficult to work with. We only are working with the heat term, which is fairly easy to measure in a calorimetry type experiment. You probably did one of those kind of experiments in Chem 1. Okay, a reminder, an exothermic reaction is one that gives off heat. The reactants have a greater enthalpy than the products, and that energy change between them goes to the surroundings. It increases the kinetic energy of the surroundings. An example of an exothermic reaction is methane burning in oxygen to give CO2 and water and lots of heat. Heat, of course, given by the symbol Q. Heat energy is given off, so the products are at a lower chemical energy than are the reactants. That's what it means to be an exothermic reaction. So enthalpy, like energy, is a state function. We can calculate the change just by knowing the enthalpy of the products and the enthalpy of the reactants and taking the change, the difference between them. So there's a diagram showing the system, the surroundings, and heat in the exothermic reaction being given off to the surroundings. Going to the other side of that table, to the endothermic reaction, that's one where the reactants are at a lower enthalpy than the products, and they get from the reactants to the products by absorbing heat energy from the surroundings. That decreases the kinetic energy of the surroundings. An example of an endothermic reaction is ice, solid water, taking on heat to melt, to become liquid water. Heat energy is absorbed, so the products are at a higher chemical energy than are the reactants. And we see the diagram there with Q coming in from the surroundings. Oh yes, a reminder, delta H of an endothermic reaction is greater than 0, and delta H of an exothermic reaction is less than 0. So when the reaction is exothermic, the kinetic energy of the surroundings increases because heat is going to the surroundings, and the surroundings become more disordered. Probability arguments say that things go to a more disordered state. If we look at our cards example, we throw a deck of ordered cards into the air, we pick them up, they're very disordered. That's what occurs spontaneously, and that is going toward more disorder. Okay, so when the reaction is exothermic, the kinetic energy of the surroundings increases, heat goes to it, and the system goes to a lower energy state. Those are both favorable. Exothermic reactions are often spontaneous. Thermodynamic considerations allows us to predict whether a reaction will be spontaneous. That is to say, will simply occur. We don't have to intervene to make it occur. So we can use thermodynamic arguments, as we'll learn in this chapter, to predict whether a reaction will be spontaneous or not. So we'll see how to do that by going on. So our next section is called Spontaneity and Gibbs Recognition. Gibbs was a scientist from the past, I believe an American scientist. A spontaneous process is one that occurs without any outside intervention. We don't have to do anything to make it happen. We don't have to change the temperature. We don't have to push it in any way to make it happen. It simply occurs. A spontaneous reaction is a reaction that occurs. Thus, we could say that a reaction that occurs must be spontaneous. Molecular systems often want to achieve a low energy state. Along these lines, it was originally thought that if a reaction were exothermic, that is, its products are at a lower energy than its reactants, then it would be spontaneous, and a reaction that is endothermic, that is, its products are at a higher energy than reactants, would not be spontaneous. But there's a problem with this idea. This reaction here, dry ice, solid CO2 forming gaseous CO2, is a spontaneous process. You know that from working in the lab. You know that a piece of dry ice will eventually sublime, it will vaporize. It's an endothermic reaction, though. It takes energy from the surroundings to be absorbed by the dry ice to cause it to become gaseous CO2. So, as our diagram there shows, the gaseous CO2 is at a higher enthalpy state than the solid CO2 because energy has come in from the surroundings in the form of heat. So we know that it spontaneously sublimes, and it does so despite the fact that gaseous CO2 is at a higher energy than solid CO2. It turns out, as we will see as we go on in this chapter, that a term called entropy, anyway, no, let's skip that for now. We'll go on. Okay, so that occurs spontaneously despite the fact that the reaction is not exothermic, it is endothermic. So there is another factor governing reaction spontaneity other than just the tendency to achieve the lowest energy state, because dry ice going to gaseous CO2 is going to a higher energy state, not a lower energy state, and yet it occurs spontaneously. Okay, so this other factor was recognized by Gibbs, that scientist, and is the tendency of a system to achieve the maximum state of disorder. So, Gibbs' recognition for spontaneity is the system has a tendency to achieve a minimum energy state, that would be favoring exothermic reactions, and the system has a tendency to achieve the maximum state of disorder. So kind of like we throw the cards in the air and they come back in a very disordered state. Now our next section is entropy, and that's where we deal with disorder and maximizing that. Entropy is the tendency for a system to achieve a maximum state of disorder. It is given the name enthalpy. So the tendency for a system to achieve this maximum state of disorder is what happens, and this state of order or disorder is called the entropy of the system, and it's given the symbol S. So kind of like enthalpy has this symbol H, entropy has this symbol S. Enthalpy has to do with energy, entropy has to do with disorder. S, entropy, is a measure of the randomness, the disorder, the number of microstates. When the enthalpy change for a process is greater than 0, so is positive, the disorder has increased. This favors reaction spontaneity. This encourages a reaction to occur. When delta S is less than 0, so is negative, disorder has decreased. This does not encourage a reaction to occur. We throw the cards in the air. They come back more disordered. We would say that process has delta S greater than 0, a positive value. That's what occurs spontaneously. I will discuss entropy and then get back to Gibbs' recognition that both the system's tendency to minimize energy and maximize disorder have to be considered together. So for now, we will look at this maximizing disorder part, the entropy part. We'll begin by looking at what's called the third law of thermodynamics. So imagine ice. Imagine liquid water in a beaker, and imagine water vapor in a flask. In ice, the atoms can only vibrate back and forth. They're locked in a lattice structure, but the atoms can vibrate relative to each other. Now, that doesn't allow for much disorder, much randomness. So we would say the entropy of the solid is low. In the liquid water, the atoms occupy a much larger volume. They can occupy the whole volume that the liquid occupies. Bigger volume means more randomness. They can also vibrate back and forth, the atoms relative to each other. The whole molecule can rotate, do somersaults, and the whole molecule can move around the beaker. Now, indeed, the rotation ability, the translation ability is hindered because there's so many nearby molecules. S is higher, though, in the liquid than in the ice. In gaseous water, the atoms can do all of this. They can vibrate, the molecules can rotate, the molecules can move about the whole volume, and the volume of the same amount of moles of water is going to be much, much larger, given that it's in the gas phase. So S is the highest for the gaseous water. So S, the entropy of any substance, increases as temperature increases. When the temperature is 0 Kelvin, that is absolute zero, the coldest it can be, the entropy is 0 in this perfect crystal state. This is what is called the third law of thermodynamics, and it turns out that's a reference point. At 0 K, S is 0. So at 0 K, the atoms in a water crystal are not moving at all. As we warm this solid, the atoms start to move and S increases. They just have more ability to move about and become disordered. As the solid is heated more, it finally melts. Its atoms now have more movement possibilities. We call those movement possibilities, the rotation, the vibration, the translation, we call those degrees of freedom. S greatly increases when the liquid forms from the solid. With more heating, it becomes a gas where it has the highest S, since a gas has even higher degrees of freedom. The gas is the most disordered. And we see that summarized in this table. So imagine a model of water. It's water in the solid phase actually has the same structure as diamond does. And anyway, the atoms only can vibrate back and forth. So the degrees of freedom is only vibrational. In the liquid state of water, the atoms can vibrate, and there's hindered rotational and translational degrees of freedom available. In the gaseous phase, the vibrational and rotational and translational degrees of freedom, those are all unhindered. They go about, plus the volume is a lot bigger, so there's a lot more randomness. And if we look at a graph of entropy versus temperature, for water, for solids, it looks something like this, where as we go to higher temperature, the entropy goes up, we hit the melting, or the melting point, it makes a jump up. Then we're in the liquid phase, and it continues to increase as we increase the temperature. And then when it has all vaporized, it makes a big leap up. And then after that, it just continues as we heat it more. All right, that next paragraph is molecules or atoms in a solid are not free to move about much, except to vibrate in place. The volume available to each molecule is only slightly larger than the molecule itself. In a liquid, the molecules can move about anywhere within the liquid volume, so the volume available to each molecule is the entire volume of the liquid. Similarly, molecules in the gas phase can move about in the entire volume occupied by the gas. Because gases occupy larger volumes than liquids, gases are always more always have more distinguishable arrangements than liquids, which in turn always have more distinguishable arrangements than solids. Thus, for a given substance, the entropy, which is called positional entropy, because we're talking a lot about volume here, kind of like where in there is it positioned. The positional entropy of a gas is greater than the entropy of its liquid, which is greater than the entropy of its solid. When a gas expands, the molecules are farther apart, and the expanded gas has more distinguishable arrangements because all the molecules have a larger volume to move in. Expansion of gases, as well as phase changes from solid to liquid and liquid to gas and solid to gas, increases the positional entropy of the system. And so here are some models. Here's a model of solid water, ice, where those atoms can vibrate only relative to each other. Here is a model of liquid water where their motion is hindered, but they can translate and they can rotate being doing things like somersaults. They, of course, can vibrate. The gaseous water, first off, we have the biggest volume, and the molecules are unimpeded. They bounce off, they hit each other and bounce off, but they can do all their somersaults and translations. So again, we have this degrees of freedom for the different phases, and we have another general sort of entropy versus temperature graph. Solid lower, liquid next, gaseous form highest. Okay, so now we will look at the entropy change of the system, and then the entropy change of the surroundings, and then the entropy change of the universe. Okay, so the system is the reaction we're focused on. The surroundings are everything else. We will first look at the system, then the surroundings. When we refer to the system, so S of the system or delta S of the system, we leave off SYS. That is to say, if we see delta S, it simply equals delta S of the system. If we're talking about the surroundings, we write either S of the surroundings or delta S of the surroundings. Delta S depends on whether the reaction produces more disorder. Delta S greater than 0 means the system has become more disordered. Of course, that's favorable for reaction spontaneity because there is the greatest number of microstates, so the highest probability of that arrangement, that most disordered one. Like enthalpy, entropy is a state function. Delta S depends only on the final, the products, and the initial, the reactant states. It's path independent. So we have that energy, enthalpy, entropy, those are all path independent. They're all state functions. So to calculate the entropy change delta S, of course we're talking about the system. We would do the products minus the reactants. And remember that when we worked with delta H in Chem 1, we could calculate it at standard conditions. So the naught that I'm showing in that delta H naught equation just represents standard conditions. 1 molar if we have solutions, 1 atmosphere if we have gases. So how we calculated delta H using the heats of formation, the thermodynamic data that are in the back of our textbook, are in the appendix of our lab manual, also are at the back of this handout. We would calculate it delta H naught, standard conditions. So it doesn't mean initial conditions, it means standard conditions. Delta H naught is equal to the sum over the moles of the products times their delta H value, that's from the reference table, minus the sum over the moles of the reactants times their delta H values. So those delta H naught of the products, delta H naught of the reactants, those are values we find in the reference table for a given chemical. We have a similar equation for delta S. Delta S at standard conditions is equal to the sum over the moles of the products times their S values at these that we find in the reference table, minus the sum over the moles of the reactants times the values for those entropies of the reactants we find in the reference table. Okay, and just as we find delta H naught in thermodynamic tables, we find S naught in thermodynamic tables. Sometimes you will see that S naught written as delta S naught, other times just S naught, and it really is a delta S naught because they are relative to the absolute entropy, the entropy at 0 K, which is 0 for every solid. Okay, where do these S naught or delta S naught values come from? They're from usually statistical calculations. We have a function that we did not talk about back when we were looking at arrangements and microstates in the beginning of this chapter. So go back to that and look at that. You'll see that for each arrangement, we could calculate an entropy change, a delta S. It is equal to K, which is a constant, times the ln of the number of ways. So we have delta S equals K, a constant, times the log of W. Well, if for a given arrangement we know what W is, in our cases it was, for example, 1 or 3 or so, then you would take the log of that W, the natural log of it, and multiply by this constant K. The constant K you will need in an upcoming lab exercise. It's given to you in the lab exercise. It's also on the exam equation sheet. Alrighty, so going on to a calculation, let's consider this reaction. Liquid water forming gaseous water at 25 degrees under standard conditions, so 1 atmosphere pressure. Okay, so before you read that next paragraph, look at the reaction and think about what you think the sign of delta S would be. So as we talked about, as we go from liquid to gas, there's a big increase in the disorder because there's so many more available degrees of freedom to the gas, and the volume is so much bigger in the gas than it is in the liquid. So along those lines, what we would predict is delta S of the system here, delta S, to be positive, a great increase in disorder. So we have here, it is expected to be positive since the gas state is more disordered than the liquid state. This increase in entropy is referred to as an increase in positional entropy, since the number of positional microstates has increased when the liquid water becomes gaseous water. The number of degrees of freedom has gone up, and the volume has gone up. Okay, so now we've predicted delta S to be positive. Now let's actually calculate it. So we would use that equation that the sum over the products, sum over the moles of the products times their value. So for gaseous water, we have 1 mole of it. So in our delta S naught equation, we have 1 mole times the entropy of gaseous water that we find in the tables, minus 1 mole times the entropy of the liquid water that we find in the tables. So our next line is delta S naught equals 1 mole times 189. The unit for S is joules per Kelvin mole. And then we do minus 1 mole times 70 joules per Kelvin mole. So the 189 we find in the thermodynamic table for gaseous water, and the 70 we find in the same table for the liquid water. So notice that moles are over moles, so the unit mole is gone, so our delta S naught comes out to be 119 joules per Kelvin. So that's our unit for delta S is joules per Kelvin, sometimes joules per Kelvin mole. The positional disorder has increased. This is favorable for reaction spontaneity. Alrighty, now we will consider liquid water forming H2 gas plus O2 gas, and we will consider this at 25 degrees Celsius. So now predict the sign. What do you think? Going from a liquid to 3 moles of gas, we would predict the delta S to be positive. The volume has increased greatly. There's more available, more unhindered degrees of freedom available. Okay, so again, it's expected to be positive since the gas state is more disordered than the liquid state, and 3 moles of gas are forming. Again, this increase in entropy is referred to as an increase in positional entropy since the number of positional microstates has increased. So next we will calculate the delta S naught. So we have 2 moles of H2 times its value plus 1 mole of O2 times its value. Those are the two products, so we do now minus 2 moles of water times its value. So we have on our next line 2 moles times 131 joules per Kelvin mole plus 1 mole times 205 joules per Kelvin mole, then minus 2 moles times 70 joules per Kelvin mole. So we found the 131 in the table for liquid water, for H2, for gaseous H2. We find the number 205 in the table for gaseous oxygen, and we find the number 70 from the table for the liquid water. So we would find that delta S naught is 327 joules per Kelvin, positive as we expected. So this is one way to find delta S. Another way is to work with a sequence of reactions and Hess's law. So that's where you're given several reactions, 2 or 3 or 4, and you have to manipulate them. You have to flip them around and so forth in order to, when you add them all together, you come up with a reaction of interest, and then you add all their delta S values for each reaction. I believe that you are doing a problem like that in the exercise on this chapter. So here the positional disorder has increased. But look at that reaction. Does liquid water spontaneously form H2 and O2 at 25 degrees? I think you know from experience it does not. Liquid water evaporates at 25 degrees given enough time, but that's still forming water. It's not forming H2 and O2. So that reaction from our experience is not spontaneous. And yet it looks like, at least if we're looking just at the system, its entropy is increasing. So what else is going on? Well, what is going on is what's happening in the surroundings. We haven't considered the surroundings, so now we have to consider the surroundings, because it's the system and the surroundings together that we have to consider to decide upon the overall spontaneity of the reaction. Okay, so now we've moved to the delta S of the surroundings. The entropy change of the surroundings is determined by the heat flow to or from the system and the temperature that this occurred at. The equation for delta S of the surroundings is delta S of the surroundings equals negative delta H divided by T, where delta H is the enthalpy change of the system, and of course that requires that the change in pressure is 0. For an exothermic reaction, we have that heat is transferred from the system to the surroundings. So the surroundings kinetic energy increases, they're moving around faster, and that makes for more randomness. So the surroundings have become more disordered. We would say whenever something becomes more disordered, its delta S increases, is greater than 0. So delta S of the surroundings for an exothermic reaction is greater than 0. But for an exothermic reaction, delta H is less than 0. That accounts for why delta S of the surroundings is proportional to negative delta H. As temperature decreases, the effect of the heat to the surroundings increases. That's why delta S of the surroundings is proportional to 1 over T. So small t means 1 over T is big, and for a low temperature, it turns out that the effect of the heat on it, the surroundings, makes a bigger difference. Okay, so here's my analogy. Not great, but it seems like it kind of helps. If we sneeze in a quiet library, we make more of an impact on others than if we sneeze on a busy, loud corner. That is, heat transferred to the surroundings at a low temperature has more of an impact on their random motion than if the heat were transferred to them if they were already hot. And that's why it goes as 1 over T. So in an endothermic reaction, heat is coming from the surroundings. The surrounding molecules' motions are less random. The disorder decreases. Delta S of the surroundings would be less than 0 because it has become more ordered. And for an endothermic reaction, delta H is greater than 0. So again, because of that, we have that negative sign in there. Delta S of the surroundings is negative delta H over T. Okay, so now we're going to be using that delta S of the surroundings equation. So let's go back to that water example where water is forming H2 and O2, 25 degrees Celsius. So let's think about what the sign of delta S of the surroundings would be. So now we're not looking at the system, we're looking at the surroundings. Since delta S of the surroundings is proportional to negative delta H, if the reaction is endothermic, we predict delta S of the surroundings to be positive. And if the reaction is exothermic, we predict delta S of the surroundings to be positive, just according to our equation for delta S of the surroundings. Since H2 is used as a fuel in some engines, it contains a lot of energy. And for H2 to form, the reaction must require energy from the surroundings and therefore be endothermic. Thus, we predict delta S of the surroundings to be negative. So we predict the reaction to be endothermic, taking in heat from the surroundings, causing the molecules in the surroundings to move slower, a little less randomly, so the entropy change of the surroundings to be negative, less than 0. Okay, now we'll calculate delta S of the surroundings. So we must calculate delta H so that we can use our equation. Delta S of the surroundings is negative delta H over T. So we find delta H at standard conditions from that summation equation, the heats of formation equation. So we have 2 moles of H2 times the heat of formation of H2, which is 0, plus 1 mole of O2 times the heat of formation of O2, which is 0, minus 2 moles times the heat of formation of liquid water. So that when we find the numbers in the thermodynamic tables, we find that it comes out to be positive 572 kilojoules, which is 572,000 joules. So yes, it's an endothermic reaction. Now we find delta S of the surroundings by taking that delta H and dividing by the temperature in Kelvin. So we have to convert 25 degrees Celsius into Kelvin, which is gives a value 298. So 572,000 divided by 298. Notice we use the joule value since it would give us otherwise a very small number if we kept it kilojoules, but we could do that. With our negative sign in the equation and a positive delta H, delta S of the surroundings indeed does come out negative. So it's negative 1920 joules per Kelvin. So it is indeed negative, meaning that the disorder of the surroundings decreases as we predicted. This is not favorable for reaction spontaneity. Alrighty, so earlier we found delta S of the system to be positive, and just now we found delta S of the surroundings to be negative 1,920, a pretty big negative number. Okay, so now we will consider the entire picture, the universe. So we have the system, we have the surroundings, values, now we'll put them together. So the entropy change of neither the system alone nor the surroundings alone tells us whether the reaction occurs. We must consider the entropy change of the universe, which is considering the system and the surroundings. Delta S of the universe is delta S plus delta S of the surroundings. Okay, so going back to that reaction of ours, we have the 2 moles of liquid water forming 2H2 gas plus O2 gas, 25 degrees. We'll calculate delta S of the universe. So we add together the delta S of the system, which is 327 joules per Kelvin, plus delta S of the surroundings, which is a negative number, so we have minus 1920 joules per Kelvin, and we get delta S of the universe to be negative 1590 joules per Kelvin. Negative, just as we predicted, because we know at 25 degrees water does not break down to H2 and O2. When delta S of the universe is less than 0 for a process, that process or reaction, we could say, is not spontaneous. It turns out it's spontaneous in the reverse direction, but of course we have to have those products as reactants to be able to react. When delta S of the universe is greater than 0, the reaction is spontaneous in that forward direction. When delta S of the universe is equal to 0, the reaction is at equilibrium. We could say the battery is dead. At a phase change, a phase transition, like when something melts or something boils, the reaction is at equilibrium. Delta S of the universe for that is 0. That comes out to delta S of the system is equal to minus delta S of the surroundings. And what we have is to use that if we have a process occurring that's a phase transition, so like melting or boiling, and let's say that we're after delta S of the surroundings, and delta S of the universe is 0, so if we can calculate delta S of the system, we can change the sign and get delta S of the surroundings. That is something that I've noticed a lot of the quiz questions in chapter 17 need you to remember. Okay, in our above reaction, delta S of the universe came out negative. The reaction will not occur at 25 degrees Celsius. Okay, I'll skip that next paragraph. Now we will get back to Gibbs recognition, which was that the tendencies of a system to reach a state of lowest energy, delta H negative, and a state of maximum disorder, delta S positive, have to be considered when predicting the reaction spontaneity. So we have to consider both the system's energy as well as the system's disorder. We have to consider those together. That was what Gibbs recognized. So that's Gibbs recognition. We're going to come up with a function that is termed Gibbs free energy change, symbolized delta G, named after Gibbs. Okay, so here's how delta H and delta S, those two components, are related. If delta H is negative, that would be an exothermic reaction. Reactants going to lower energy. That's favorable. If delta S is positive, that means the system is becoming more disordered. That's favorable. Is the reaction spontaneous? Yes, since both the two factors we have to consider, the energy and the entropy, are both favorable. Yes, the reaction is spontaneous. It turns out it's spontaneous at all temperatures. If delta H is positive, so that would be an endothermic reaction that's climbing to higher energy, and delta S is negative, that means becoming more disordered. Both of these oppose spontaneity. They both disfavor it. So no, the reaction is not spontaneous, and it's spontaneous at no temperatures. It just will not occur. But if we have a positive delta H, so going to higher energy, but a positive delta S, so becoming more disordered, it would be or could be spontaneous if the entropy component dominates, if the positional disorder dominates. It turns out this occurs at high temperatures. If, on the other hand, delta H is negative, so an exothermic reaction, lower energy, and delta S is negative, so that means becoming more disordered, it can also be spontaneous if the energy component dominates, if the delta H part dominates. It turns out that one occurs at low temperatures. So what we've got here in these four scenarios, the delta H, delta S combination scenario, we have situations for different reactions, and they can be spontaneous or not depending upon their delta H and delta S values and signs. Okay, so in these latter two situations we looked at, delta H positive, delta S positive, and delta H negative, delta S negative, we cannot simply say if the reaction is spontaneous or not. We must know the magnitudes of delta H and delta S and use what's called the Gibbs free energy change expression. Gibbs free energy change expression is delta G is equal to delta H minus T delta S. So if we take that first situation, delta H negative and delta S positive, we have negative minus a positive, we end up with a negative overall. We get a negative value for delta G, we get delta G less than 0. That reaction is spontaneous. We see a diagram there showing Gibbs free energy versus time, and there we have reactants at higher Gibbs value dropping down to products at lower Gibbs value. It looks kind of like an exothermic reaction, except instead of having H versus time, we have G versus time. G is not just considering energy, it's considering everything. It's considering energy and disorder, energy and entropy. Instead of calling it an exothermic reaction, we call it an exergonic reaction. So a spontaneous reaction we could say is an exergonic reaction, or an exergonic reaction is one that occurs spontaneously. Delta G also has another meaning. It's called Gibbs free energy change, so it's got to do with energy. It describes the maximum usable work in a process. So it would be the maximum. In practice, it is substantially less. In our second situation, where delta H is positive and delta S is negative, we end up with positive minus a negative, so we end up with a positive value overall. There, delta G is positive, it's greater than 0, the reaction is not spontaneous. And there's a diagram showing reactants at low Gibbs value going to higher Gibbs value for the products. The reaction is not spontaneous. Instead of calling that an endothermic reaction, we call it an endergonic reaction. It is spontaneous in the reverse direction only if we happen to have the products as reactants. Delta G has a meaning. It means the work, the minimum energy that must be supplied to make that process go. It's describing the energy that we must input to make the process go. In practice, a lot more energy is needed. Okay, now let's go back and look at our energy column. So let me get to the right spot. Okay, so we have our Gibbs free energy change expression. Delta G is delta H minus T delta S. So in our first situation, both favor spontaneity, both delta H and delta S favor spontaneity, so it's going to occur no matter what. In our second situation, delta H positive, delta S negative, they both disfavor spontaneity, so that's going to occur, or is not going to occur at any temperature. In the third situation, delta H positive, delta S positive, we have that the delta S favors spontaneity. Delta H does not favor it. So if we can enhance the T delta S term, then we can make that happen. And that's why that situation occurs for high temperatures. Our last situation, where delta H is negative, which favors spontaneity, delta S is negative, which disfavors spontaneity. We want to enhance the delta H term, so we want to de-enhance the T delta S term, so we want to go to low temperatures. Okay, so now we're looking at a specific reaction, the liquid water forming the H2 and the O2, again at 25 degrees. Earlier, we calculated delta S of the universe to be negative 1590 joules per Kelvin, given delta S of the system to be 327 joules per Kelvin, and delta S of the surroundings to be negative 1920 joules per Kelvin. Since delta S of the universe is negative, the reaction is not spontaneous. Although delta S is positive, there's an increase in positional entropy. Delta S of the surroundings is very negative due to the endothermicity of the reaction, reducing the kinetic energy of the surroundings and making them more disordered. Okay, so we're now going to calculate delta G. So we can decide if a reaction is spontaneous by calculating delta S of the universe, or we can calculate whether a reaction is spontaneous by calculating delta G. Delta S of the universe requires we know delta S of the system plus delta S of the surroundings. To calculate delta G, we need to know delta H of the system and delta S of the system. So it kind of depends what we're asked to do and what information we have, which way we go, whether delta G or delta S. Here we're asked to calculate delta G. So earlier, much earlier, we had calculated delta H for this water to H2 plus O2 reaction to be that big number 572,000 joules. We had calculated delta S, as we've got written up here, to be 327 joules per Kelvin. So we just use that equation, put in delta H, put in T, put in delta S, and we end up with delta G equaling this 475,000 joules, which is 475 kilojoules. So it's positive, as we expect. The reaction is not spontaneous. Delta G is a state function. We can also calculate delta G using that summation version of the equation. Just as with delta H, we can use that summation equation and the heats of formation. For delta S, we can use that summation equation and the S values we find in the thermodynamic tables. Well, we can do the same with delta G using what's in thermodynamic tables and that summation equation. So looking at our reaction, we have 2 moles of H2. We look up the value for H2. It turns out it's 0. We have 1 mole of O2. We look up the value for O2, which is also 0. And then we have minus 2 moles of water. We look up the value for water, which is negative 237 kilojoules per mole. We do all the multiplication, addition, and we get 474 kilojoules. So pretty similar to what we found using the above data. We could also calculate delta G using a sequence of reactions and Hess's law. And I think on that exercise for this chapter, either you calculate delta S using Hess's law or delta G using Hess's law and a sequence of reactions. Okay, now that reaction is not spontaneous. We have established that by knowing delta S of the universe to be negative or delta G to be positive. So both indicate it's not spontaneous. But at what temperature is it spontaneous? So for a reaction to be spontaneous, we have to have delta G equaling a negative number. Now, if we look at our delta G equation, we have delta G equals delta H minus T delta S. T, when delta G is positive, the reaction's not spontaneous. By changing the temperature, if it can just go negative, then it becomes spontaneous at that new temperature and a bunch of other temperatures around that temperature. So what we can do is set delta G equal to 0 and solve for T, and either say it's spontaneous at temperatures above this or it's spontaneous at temperatures below this. Okay, now we set delta G equal to 0 and we solve for T. So we get T is equal to delta H over delta S. We put in our delta H from above, 572,000 joules. We put in our delta S from above, 327 joules per Kelvin. The joules cancels out. We have 1 over Kelvin, which is Kelvin, and our number is 1749. Now, if we go back up here to this reaction, and we see that delta H being positive is not favorable, but delta S being positive is favorable, what we want to do is enhance the T delta S term. So to enhance it, we increase the temperature. So that's why we would say that at temperatures above 1749 Kelvin, the reaction is spontaneous. Just a reminder of kinetics, we can say that at temperatures above this, the reaction could occur, but we're not saying anything about how fast it occurs. Okay, so a summary of all this stuff is, if delta H is positive, that's endothermic, that disfavors spontaneity. But if delta S is positive, that favors spontaneity. So we have that negative sign there, negative T delta S, as part of our equation. To enhance what favors, we want high temperatures. If we have delta H negative, that favors, but delta S negative, which disfavors, we want to de-enhance the T delta S term, so we want to go to low temps. If delta H favors being negative, if delta S favors being positive, that's going to be spontaneous at all temperatures. And if delta H is positive, which disfavors, and delta S is negative, which disfavors, that will not be spontaneous at any temperatures. Alrighty, now we come to the second law of thermodynamics. So we have the first law of thermo, energy is conserved. We have the third law of thermo, entropy is 0 at 0K, and so we must have a second law. And the second law is that when the energy of the entropy of the universe is greater than 0, so is positive, the universe is getting more disordered, entropy is always increasing. That is the second law of thermodynamics. Notice that delta S greater than 0 for spontaneity, delta G less than 0 for spontaneity. Those two have the negative sign involved in them. One below 0 spontaneous, the other above 0 spontaneous. So let's see how they're related. Going to our Gibbs free energy change expression, we have delta G equals delta H minus T delta S. Dividing both sides by T, we have that second line. Changing the sign, we have the third line. So looking at negative delta H over T, that's delta S of the surroundings. Delta S is just delta S of the system, of course. And when we have delta S of the surroundings plus delta S of the system, we have delta S of the universe. That is to say, delta S of the universe is equal to minus delta G over T, or we could say delta G is equal to minus T delta S of the universe. So that shows the relationship between delta G and delta S of the universe. So a couple examples of this in practice are looking at a hot pack, and then we'll look at a cold pack. Hot packs, typically there are two designs, one containing a solid, such as calcium chloride or magnesium sulfate, and another containing a supersaturated solution, like this sodium acetate. So in the solid salt, like the calcium chloride dissolving, okay, so what we have is a rectangle divided into two compartments. In one compartment we have water, in the other compartment we have the solid, the calcium chloride. When we nudge it, kind of squeeze it, what we do is we break the compartment between the water and the solid, allowing the solid to dissolve in the water. And it automatically, when we break the barrier, it automatically happens. It is spontaneous. It gets warm. How do we know it's spontaneous? Because it's getting warm. Now let's look at this from the perspective of our delta S of the universe equation and our delta G equation. So looking at delta S of the universe, which is delta S plus delta S of the surroundings. If we look at our reaction, solid forming aqueous, we would predict an increase in entropy, in positional entropy. So that favors spontaneity. The reaction is exothermic, gives off heat to the surroundings disorder increases. That favors. So that's why that comes out positive. If we look at it from the perspective of the delta G equation, delta H is negative, it's exothermic. Delta S is positive, more disordered. So we have a negative delta H minus T times a positive delta S. They both favor, and that's how it comes out negative. So that's why it's spontaneous. Now for the supersaturated solution, we have an aqueous solution actually having so much salt in it that if we just kind of irritate it, if we just kind of bump that pouch that's soft, it will start becoming hard. The solid will come out of solution, and in this reaction it gives off heat. So it's an exothermic process. So looking at our delta S of the universe equation, we have if we're looking, no, let's look at delta G of the delta G, the Gibbs free energy first. So delta H is negative, it's exothermic, but when we look at that reaction, we see that aqueous is becoming solid. We expect it to have more order, so the delta S to have decreased. But delta H is negative and it favors spontaneity while the delta S disfavors it. But it must be that the delta H is more favorable than the delta S is unfavorable, because it is spontaneous, it happens, so we know that it occurs. Looking at the delta S of the universe side, we have the delta S part being negative, as we talked about before, that disfavors, but we have heat given off, so the surroundings become more disordered. Delta S of the surroundings is positive, that favors, and it must be that the favorable part dominates over the disfavorable part, because we know delta S of the universe is positive because the process happens. So that's a hot pack. Cold packs, are similar to the solid hot packs in having two compartments, a solid and then water. We break the barrier, the solid dissolves. If it does so endothermically, then we have a cold pack. Looking at our delta S of the universe, we have, if we look at the reaction, delta S is, we expect positive, favoring spontaneity, becoming more disordered. But delta S of the surroundings, we expect to be negative because heat energy is having to go from the surroundings into the system to cause that dissolving to occur. And that means the surroundings are becoming slower, more ordered. But we know that when we break that barrier, the cold pack gets cold, so we know delta S of the universe has to be positive. So it must be that the delta S of the system is more favorable than the delta S of the surroundings is unfavorable. Looking at the delta G expression, we know delta G is negative, it is spontaneous. Delta H is positive, disfavors, but delta S is positive, which favors, and it must dominate over the other one. So those are the two ways to look at those, giving us basically the same information. We have two more delta G functions, and from our previous chapters, we had K, the equilibrium constant, and Q, the reaction quotient. So looking at reactants to products, K would be products concentrations divided by reactants concentrations, of course raised to whatever are the appropriate coefficients, stoichiometric coefficients. And Q would be the same thing except at initial conditions. So incorporating our current chapter and that material into this table here, if delta G is less than 0, the reaction is spontaneous and it goes to the right, it goes to products. From our last chapter, if a reaction goes to products, we know that that means that Q is less than K. Remember that thing that we drew, that visual we put, if Q is less than K, we put it to the left side. It's going to go to K, so it goes to the right, goes towards products. If delta G is greater than 0, it's not spontaneous. It actually would be spontaneous in the other direction if we had those products as reactants. And if we think of that same visual, we would put Q on the bigger side of K in order that when Q goes to K, it's going toward the left. If delta G is 0, it's at equilibrium. Q is equal to K. The battery is dead. So there's a relationship of delta G and Q. I tried to show you in that table above, that discussion there. What that relationship is, delta G is equal to delta G naught. That naught does not mean initial, it means standard conditions, plus RT ln of Q. So what we have is delta G equals delta G naught plus RT ln of Q. So delta G naught is the Gibbs free energy at standard conditions. RT is the non-standard conditions correction. Alrighty, so let's see how we use that. We're going to come up with a few equations. So looking at our delta G equation we just have up there, we have delta G equals delta G naught minus, or delta G equals delta G naught plus RT ln of Q. We would say that if we are at equilibrium, delta G is 0, so let's put that there for delta G, put a 0, equals delta G naught. Now, if we are at equilibrium, then Q has gone to K. So we replace Q with K. So that's what we've done. We've got 0 equals delta G naught plus RT ln of K. Or if we solve for K, the equilibrium constant, we have K is equal to E to the minus delta G naught over RT. Alrighty, now we're going to use that by looking at this problem here. We have the reaction N2 plus 3H2 in equilibrium with 2NH3. That's the Haber process. We talked about that in a previous chapter. These are all gases at 25 degrees Celsius. Calculate delta G when the partial pressure of each gas is 0. Okay, so looking at our equation at the top of, hopefully it's at the top of your screen there, delta G is equal to delta G naught plus RT ln of Q. If we are at 1 atmosphere pressure, we're at standard conditions. So at standard conditions, Q, which is products over reactants, everything is 1. Q is equal to 1, and that whole RT ln of Q term is gone. So delta G is delta G naught. We find delta G naught by using the thermodynamic data. So we take 2 moles times the value for NH3, which is, according to the table for ammonia, negative 17, minus 1 mole times the N2 value, which is 0, plus 3 moles times the H2 value, which is also 0. So the negative 17, the 0, those come from the thermodynamic tables in your textbook, at the back of this handout, in the appendix for your lab manual. Delta G naught, that is delta G at standard conditions, is negative 34 kilojoules. The unit for the 17 is kilojoules per mole, and the unit for the 2 in front of it is moles. So now we have the same reaction, but the partial pressures of the N2 and the H2 are increased to 2 atmospheres, 2.0 atmospheres. So we have 2 atmosphere H2 plus 2 atmosphere N2 plus 2 atmosphere H2 reacting to produce ammonia at 1 atmosphere. So now we're calculating delta G. Now we will use that equation that's still, for me anyway, at the top of the screen. We expect the delta G to be a bit greater, and since this is exergonic, we expect it to be a larger negative number when we have higher pressure on the reactant side. Think about the Le Chatelier's principle. If we've increased the amount of each reactant, we're going to expect it to go farther to product, and it'll be reflected in a more negative value for delta G. So that's our expectation. Okay, so we use that non-standard conditions equation. Delta G is equal to delta G naught plus RT ln of Q. We calculated delta G naught just above to be negative 34 kilojoules, or negative 34,000 joules. I converted to joules because R, which is this 8.314 joules per mole Kelvin, has the unit joules in it, so I had to be consistent. So we have negative 34,000 joules plus 8.314 joules per mole Kelvin times the temperature in Kelvin, 298 Kelvin, times the log of Q, which is, let's get our reaction back here. Our reaction is that we have 2 NH3 in the top, so we have the 1 atmosphere pressure squared, divided by N2, its value is 2 atmospheres, divided by H2, which has a value of 2 atmospheres, cubed because of our stoichiometric coefficient there, So we calculate delta G to be negative 41,000 joules, which we could convert to negative 41 kilojoules. And you can ignore the mole term, because if you do look at units, it doesn't totally work out that the mole goes away, but technically it's really there, because really delta G naught, even though we don't always write per mole, but they're technically per mole of reaction. As the reaction proceeds, Q becomes less negative. It becomes, Q increases, ln of Q increases, and that is being added to a negative number, and so that causes delta G to become less negative, to become more positive, and to go to 0. And that would mean the reaction's done, it's in equilibrium. If it were a battery, we would say the battery is dead. Batteries are simply reactions, spontaneous reactions that we've tapped into to get tap into the voltage, and so we can utilize them, get energy from it. Okay, so we're still using that same reaction, N2 plus 3H2 in equilibrium with 2 NH3, all gases at 25 degrees Celsius. So we're asked to calculate K. So we have that equation, delta G naught is equal to minus RT ln of K, or we can write it as K is equal to E to the minus delta G naught over RT. Or as I've written, E is equal to EXP of delta G naught over RT. So K equals E to the negative 34,000 joules. Notice I had to once again convert to joules, divided by 8.314 joules per mole Kelvin, divided by 298 Kelvin. So we end up with K equaling to 9.1 times 10 to the 5th, a pretty big number. That means that the reaction goes far toward products at standard conditions. It doesn't tell us how quickly it happens, though. That's kinetics. Now, as we go through these problems, be sure to stop the video whenever you need to, or look back over your notes later to make sure that you are able to do all these calculations. Okay, now we have a new reaction. N2O4 in equilibrium with 2NO2, they're all gases. From the thermodynamic table, we have that delta G of NO2 is in the table 51.3 kilojoules per mole. Delta G from the table of N2O4 is 97.9 kilojoules per mole. So we're going to calculate K. So what we have to do is calculate delta G, and that is equal to 2 times 51.3 minus 1 times 97.9. The units are kilojoules, and we get 4.7 kilojoules. Now we can use K is equal to E to the minus delta G over RT, and we put in our value for delta G. We needed to convert it into joules. It's a positive value. Anyway, our equation has the negative in it. So we have E to the negative 4700 joules divided by 8.314 joules per mole Kelvin divided by 298 Kelvin. And we get K equals to 0.15 atmospheres. But we can leave off the atmospheres. Okay. I wrote atmospheres, not that that's the unit there, just that it's actually technically Kp as opposed to K. Okay, a reaction summary, equation summary. So we have so many equations we've worked with. Look over those carefully. Make sure that you would know how to work with them. Get started on the homework problems. Here are those thermodynamic data tables that I referred to a lot as we went through this chapter. It's by substance, alphabetical. So if you're working with aluminum, go toward the top and hopefully you'll find your aluminum compound in there. If you're working with carbon in a compound, look under carbon. If you don't find it there and the compound has hydrogen, look under hydrogen, look under oxygen. You'll probably find it under carbon, but just be willing to scout around. The first column of numbers is those delta H values that you would have used in Chem 1. The next two columns are the delta G values, the S values. Those are new from this chapter, but that's where we find them all. Notice what the units are of all that data. Alrighty, so go back through your handout notes by yourself as slowly as you need to. Go back through this video as many times as you need to, and get started on the homework problems. You can also get started on the lab exercise for this chapter that you will be turning in. And eventually the quiz for this chapter will be open, and check the dates when it's open in Canvas to make sure that you get through all that work. Okay, that's it for this chapter.